Testing. 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 It is the age of the test. I'm not actually getting any audio. Row. Okay, I am getting audio. It's just not very good. Test. Okay. I think that's fine. Nisio tried to read through this paper from start to finish. It was very confusing. I don't know a lot about diffusion. Plenty of denoising left to do in my mind. I like the denoising. That's a good pun. All right, so welcome to another Hupo stream. We're going to be looking at a paper called RAPHAEL Text-to-Image Generation via a Large Mixture of Diffusion Paths. So this is going to be an image generation, text-to-image paper. I think most notably to me is the amount of compute that they used for this. 1,000 A100 GPUs for 2 months. And then supposedly they have state-of-the-art, but FID score is a little bit weird anyways. So, yeah, this is coming out of SenseTime's research. SenseTime is a very strong computer vision company from China. I think they actually have these huge government contracts, and they're the ones that have all the face detection cameras that run in the cities. So basically, extremely strong computer vision company, and then I don't know what the relative ranking of University of Hong Kong is with respect to other institutions in China, but it's basically the Chinese Stable Diffusion, and it looks pretty good. So, kind of interesting. They do have this page, and I did notice that they had here a comparison to different models. So they have RAPHAEL, which is this one here. They have Stable Diffusion, Deep Floyd Dolly. I've never heard of Ernie VILG, but it doesn't seem like it's very good anyways. So I was like, hey, you know what's a good way to kind of start this stream is to compare this stuff to Midjourney. So that's what I did. I typed some of these into Midjourney. And for example here, I typed this exact one, a sign that says RAPHAEL, into Midjourney. And it actually looks that Midjourney can't spell. None of these say RAPHAEL. They're kind of like close, but not quite. And that's what you kind of see here, where actually Deep Floyd, Dolly, Ernie, none of these can really spell other than Stable Diffusion XL and then RAPHAEL. So it does look like it can spell better than Midjourney, but I don't know. This is a car playing soccer digital art. This one is obviously a little bit nonsense, but I don't know. I would say these are kind of on par with this one here. And then I tried to get this one here, a parrot with the pearl earring. So this is a actual painting by Vermeer. Let's see if it'd take a second. So I like whenever Midjourney, they actually show you the intermediate results of the diffusion. So this is basically intermediate time steps as you remove more and more noise from the image. So I feel like the Vermeer style is there, but this is not a parrot that has a pearl earring. Maybe this one a little bit. I would agree that the RAPHAEL version of this is a little bit better for sure. This version here. Okay, so kind of just with our little tiny evaluation that we did right there in about 5 minutes, it seems like it's actually pretty good, and it might even be better than some of the available stuff. And they do show that you can fine-tune it. So here they show a training set of some images from some anime that I don't know about, and then they train a LoRa, a low-rank adapter, with 32 images on RAPHAEL and then Stable Diffusion, and then they compare them. I would say that the Stable Diffusion one kind of seems fine. I don't really understand what they're saying here. Only RAPHAEL preserves the concepts in the prompts. Flower, knight, sword, none. Okay, so I think what they're trying to say here is that when you fine-tune it and then you try to do a text-to-image, the Stable Diffusion is not going to try, like, there's no flowers here is basically what they're saying. Where the Stable Diffusion, if you fine-tune it, it'll just overfit to this kind of like little character, and it kind of only does this little character. Versus the RAPHAEL model, you can see it still has the sword, the background is the knight, and so on. So, okay. Looks pretty good to me. Let's get going into this paper, see what they're doing. Spelling examples are probably tempting to cherry pick. Yeah, 100%. I agree with you, Nisio. All examples are cherry picked. Like, pretty much anytime you look at a paper, that these right here, these are the best possible examples. So, I don't know. But everyone's doing that. So, whenever you see a Stable Diffusion paper, that's also the best examples. So, you kind of got to go with that. This is kind of cool. I've never seen this before. They have a little quote. They have a quote from Raffaello Sanzio da Urbino. I don't know who this is. Probably some kind of Leonardo da Vinci type character. Probably painted some stuff in Renaissance Italy, but that's kind of cool. I've never seen a quote in a paper like that. All right, text to image generation has recently witnessed remarkable achievements. We introduce a text conditional image diffusion model. So diffusion is the kind of like the model architecture. It's basically a process where you remove noise over a series of time steps, and you can condition that noise removal on a piece of text, and that's kind of the magic of image generation. Generates highly artistic images which accurately portray the text prompts encompassing multiple nouns, adjectives, and verbs. This doesn't have any meaning. These are just kind of qualitative judgments, so there's no actual scientific definition for accurately portraying and highly artistic. So those don't really mean anything. This is achieved by stacking tens of mixture of experts layer. Okay. So now they're going a little bit deeper into maybe what makes them different from the OG Stable Diffusion. So mixture of experts, it means, so sometimes people do this in, for example, Kaggle competitions where they'll have multiple models that are trained to do the same task, and then you feed them the same input and they'll produce slightly different outputs. And you pick a bunch of models that are maybe slightly different architectures, maybe have slightly different biases, slightly different priors, and in that way you can get a little bit more kind of variety in the answer. And sometimes by having this kind of mixture, right, multiple models, aka experts, you can get a better answer by taking kind of the best out of all the experts rather than just finding the highest performing model and only using the output from the highest performing model. So that's probably not what they're doing here, but we'll see. Space and time. Space is going to be in the dimension of height and width of the image probably, and then time is going to be in the dimension of the time steps. Enabling billions of diffusion paths, routes from the network input to the output. Okay, so the way they're saying this, if you actually look at the original Dropout paper, I think it might be this one. PDF. So Dropout is a regularization technique that's very popular. It's a little bit old now, and sometimes it goes in and out of fashion. So there was a time when it actually went out of fashion, and now I think it's actually come back from fashion. But in Dropout, you basically have your little neural net, and every single neuron is kind of connected to every single other neuron in the layer ahead, right? That's what the whole fully connected neural network, right, means. It's fully connected. All of them are connected. And whenever you're doing dropout, you basically have a random chance of dropping out, aka zeroing specific neurons during training. And what this does is it forces the neural net to use all of its capacity. So if you don't have dropout, sometimes what ends up happening is that one of these neurons kind of ends up dominating, and the other ones kind of get ignored. So basically the neurons in the layer on top just learn that they just need to focus on this neuron here and ignore the other neurons. And you don't want that, right? You want the model to use its kind of full capacity. So by having dropout, sometimes that neuron becomes zero, and then the neurons in the layer above have to learn and figure out how to use these other neurons, the signal coming from these other neurons. So it's a type of regularization, and generally it makes the learning process bit better. But why am I talking about dropout? All right, the reason I'm talking about dropout is that there's one specific area of this paper where they mention that, let's see if I can find it, experts. Mixture. Yeah. So, that's not exactly what I want, but it might not even be in this paper. But basically, they make this analogy that whenever you're actually doing dropout, what you're doing is you're training a bunch of different models that are all sitting within the same model, right? So rather than a single neural net where it's fully connected and it's been fully connected the entire time during training, when you're doing dropout, you're effectively training a bunch of sub-networks that are kind of like all weaved in together. And then whenever you do inference and you don't have any dropout, whenever you're actually using this neural network, aka in inference mode, you're not going to have any dropout. What you're kind of doing is you're aggregating the result of many different models that are all kind of embedded together, right? Embedded maybe not the right word to use because that has a formal definition, but like all these kind of sub-networks are all kind of acting together, and that kind of it kind of rhymes with this idea of a mixture of expert models. So that's why I brought that up, but hopefully that didn't confuse people. Each path intuitively functions as a painter for depicting a particular textual concept onto a specified image region. So specified image region at a diffusion time step. So specified image region is going to be this space MOE, right? And then time MOE is going to be this diffusion time step. Comprehensive experiments reveal that... Ooh, we got a comment here. Appreciate you always explaining the acronyms and terminology. Yeah, sometimes I go back and forth. Sometimes I feel like I'm a little bit too much of a mansplainer here, and I just kind of sit here and explain. It takes me like 20 minutes to get through the abstract, but then I end up reading YouTube comments where people are like, I love that you explain different terms. So I don't know. I kind of end up doing both. In dropout for transformer, are complete tokens dropped out or elements within each token vector? I don't actually know. Let me see. Dropout in transformers. We apply dropout at the output of each sublayer, so it looks like they're doing the dropout at the in-between. Transformers image. Not the transformers I wanted. Neural net. Yeah, so I think they do the dropout here. So basically in between the multi-head brick and then the next one, probably this feed forward has dropout. Sublayer, dropout, layer norm. But this isn't actually even how they do it anyways. I think the layer norm is actually before the attention mechanism now. So basically they drop that out. And you wouldn't want to drop out before the layer norm. That seems kind of weird. Yeah. You basically, the whole point of dropout is you want to force the neural net to learn to use more of the signal, right? It's... Okay. Comprehensive experiments reveal that RAPHAEL outperforms recent cutting-edge models such as Stable Diffusion in terms of both image quality and aesthetic appeal. I don't know if... we'll see what kind of benchmarks they use, but to me, like, image quality benchmarks are a little bit bogus anyways. RAPHAEL exhibits superior performance in switching images, Japanese comics, realism, cyberpunk. A single model with 3 billion parameters. So, is that a lot of parameters? What's the biggest VIT that you can get? VIT hugging face. VIT, so a VIT is a vision transformer, model sizes. 632 million parameters. Yeah, so actually 3 billion is pretty big. How many parameters is Stable Diffusion? Stable Diffusion parameter count. Stable Diffusion is 890 million parameters, and then DALL-E 2 is 3.5 billion parameters. Okay, so this is roughly at the scale of DALL-E 2, but a little bit bigger than Stable Diffusion. But model size isn't necessarily everything, right? And I think you can usually tell, like, for example, here, DALL-E 2, 3 billion parameters, right? But look at that. It can't even spell RAPHAEL, versus Stable Diffusion can spell it. I don't know if Stable Diffusion XL is bigger or not. It probably actually is. So this is probably the size of just standard Stable Diffusion, but then Stable Diffusion XL is probably bigger than that. Yeah, so they trained this on 1,800 GPUs, which is fucking gnarly. We're talking millions of dollars there. RAPHAEL significantly surpasses its counterparts on whatever this benchmark is here, VILG 300. We believe that RAPHAEL holds the potential to propel the frontiers of image generation research in both academia and industry, paving the way for future breakthroughs in this rapidly evolving field. Okay, so, I mean, hopefully that means you open source it, but if they didn't open source it, they're not propelling anything. They're just propelling their profits. Okay, comparison. This is the image we just looked at. Given similar prompts, the words that our human artists yearn to preserve within the generated images are highlighted in red. Yearn to preserve, kind of an interesting choice of words there. These images are not cherry-picked. Do we trust them? The VIT and the Pali X paper is 22 bill. Yeah. Monster models. But I don't know if I trust them that these images aren't cherry-picked. I think there's too much pressure on researchers to produce results for them to not cherry-pick. Blah, blah, blah. Better zoom in 200%. Cool. All right. Recent advancements in text-to-image generation, such as ImageGen, Stable Diffusion, DALL-E 2, eDiff-I, Ernie VILG 2.0. What the fuck is this VILG that they keep referencing here? Okay, so this is why they keep referencing this, is because this is probably them. No. Give me this. Ernie VILG 2.0. Ernie VILG 2.0. Large-scale Chinese text-to-image diffusion model. So it's like, I bet you some of these names are the same, actually. Let's see. Baidu, School of Computer Science, Wuhan. Okay, so this is actually two different groups, but it's the other groups. I wonder if some of these people are the same. Let's see. Zeyue Shui. Okay. It might be different people, but it's the other Chinese model. have yielded remarkable success and found wide applications in computer graphic. Despite the substantial progress made in text-to-image diffusion model, there remains a pressing need for research to further achieve more precise alignment between text and image. As illustrated in Figure 1, existing models often fail to adequately preserve textual concepts within the generated images. This is primarily due to the reliance on classic cross-attention mechanism for integrating text descriptions into visual representations. Okay, resulting in a relatively coarse control of the diffusion process. Okay, and leading to compromised results. Okay, so they're kind of saying that the problem with diffusion models comes to the way that the text is used to condition the diffusion process, and they're calling it coarse. So we'll see exactly what this means. We introduce RAPHAEL, which yields images in a superior artistry and fidelity compared to prior work. An acronym that stands for Distinct Image Regions Aligned with Different Text Phases in Attention Learning. So attention learning, probably still using some kind of transformer. Different text phases, I think this probably refers to the different tokens in the text sequence. And then image regions, they keep talking about this kind of like spatial kind of situation going on here, different regions of the image. So we'll see exactly what kind of prior they use to do that. For example, like ConvNet has a translation invariance prior with the fact that the feature map moves across the image. In a VIT, a vision transformer, there's a little bit of a prior here where you basically flatten the image into this sequence of patches. So by flattening it like this and saying that this part of the image goes after this part of the image goes after this part of the image, you're kind of introducing the same prior that you have in a ConvNet, where you basically go from the top left and then you go left to right and then you go down. So a lot of vision stuff actually has the same prior, this kind of like left to right and then top to down. So I wonder if they're doing something like that. We observed that different text concepts influence different image regions during the generation process, and the conventional cross-attention layer often struggles to preserve these varying concepts adequately in an image. To mitigate this issue, we employ a diffusion model stacking tens of mixture of expert layers, including both space MOE and time MOE layers. The space MOE layers are responsible for depicting different concepts in specific image regions, and the time MOE layers focus on painting these concepts at different diffusion time steps. I would say diffusing, removing noise conditioned on the text. This configuration leads to billions of diffusion paths. Naturally, I mean, any neural network has billions of paths. Like, I don't think that's like kind of an eye-opener. I don't think this is some kind of crazy statement. Like, in any neural net, there is like a billion different paths that information can travel, right? So what does it mean to have billions of different paths in a neural net? Naturally, each path can act as a painter responsible for rendering a particular concept to an image region at a specific time step. The result is a more precise alignment between text tokens and image regions, enabling the generated images that accurately represent the associated text prompt. This approach sets RAPHAEL apart and even sheds light on future studies of the explainability of the generation process. So it kind of sounds like they're setting up this thing where they're going to have different parts of the model are going to be like basically focused on one specific time step and one specific region of the image. I don't know how different that is from a normal diffusion model. Like in a normal diffusion model, is every part of the model contributing a little bit to every single step? Or do you have different parts of the diffusion model contributing unequally to different parts of the diffusion process? I don't know. I don't know if this process that they're describing here is what happens in a normal diffusion model anyways. Performs such as blah, 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 exhibits superior performance. New state-of-the-art with a zero-shot FID 30K score on the COCO dataset. RAPHAEL, a single. So I think what they're meaning here is COCO dataset is common objects in context. This is a dataset for image segmentation, image classification that was released by Microsoft a very long time ago. It's kind of COCO dataset. It's old now, but it's still quite representative. This is what COCO images look like. Kind of generally object-centric, right? So there's generally like something right in the middle of the image. But I think what they're trying to say here is that zero shot means that they didn't do any fine-tuning specifically on COCO, and I think they probably tried to generate images, and then they compared the images that were generated to the actual images on COCO, and they said how similar are the images that are generated to the images in COCO, aka how capable is the model at producing images from within a specific distribution. And FID is a metric, it's a distance that allows you to compare two different images, right? So they get a state-of-the-art score there. RAPHAEL, a single model with 3 billion parameters trained on 1,000 A100, significantly surpasses its counterparts in human evaluation on the VIL G300. Capable of generating images with fucking monster resolution here, 4096 to 6144. So most image generation actually generates either in latent space and then uses an pre-trained image encoder to turn that latent back into an image, and then even after that, usually the image is not super high resolution, and you'll use like some kind of up resolution model to do it. So generally, when you see high resolution images from text to image models, there's multiple steps there. You're going up from a latent into an image with a different model, and then you're also going from that image up to a higher resolution version of that image with a different model. So there's like multiple steps with different models in order to get to a very high resolution. But we'll see what they do here. I assume they're probably going to be doing diffusion in the space of the latents, because doing diffusion in the space of 40,000 by 61,000 or 4K by 6K images seems outrageously slow. So we'll see how they get to that, and whether they're just using an up resolution model. They wait to section 4 to say that they're doing diffusion in the latent space. Okay, so I mean, if they're doing diffusion in the latent space, then whatever they're using to convert those latents into images, that's the actual model that's generating images, right? Like using a VAE. Yeah, are they actually doing anything with that VAE, or do they just use a frozen pre-trained VAE? That's the question. Oh, actually, here you go. Boom. They answer it. Maybe I should read the entire sentence before I go on a rant here, but okay, the way they get these giant resolution images is they actually use a SRGAN model, a super resolution generative adversarial network. And the word tailor-made here means that they probably trained it as part of this process. So it's their own custom super resolution GAN. We propose a novel text-to-image generator through the implementation of several carefully designed techniques. We thoroughly explore the potential for switching images in diverse styles, extensions using LoRa, ControlNet, and SRGAN. Okay, so here are a bunch of other cool things that people have done in the image generation space. LoRa's are these little tiny matrices that you basically kind of parasitically attach to your existing model, and then you can fine-tune these LoRa's without touching the original model, and you can get the original model to do slightly different things. We've read a bunch of LoRa papers. If you guys are interested, definitely check those out. ControlNet is this idea where basically you can condition the generation on certain types of images, like edge detection images. Let me see if I can find a good picture for this. ControlNet, yeah, this right here. So you can condition the generation on something like a normal map or a segmentation map or a depth image or pose detection. So gives you control over the generation, aka control net. We will release a programming API to the public. Okay, programming API to the public does not mean that they're releasing the model weights. What this means to me is that they're just releasing the ability to use RAPHAEL, but it's probably going to be something like Midjourney, I guess, where you're not actually going to get access to the model. You just have the ability to generate images, probably for some fee. Holds the potential, blah, 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 blah. Okay. We present the necessary notations for denoising diffusion probabilistic models, DDPM, for text image generation, given a collection of n images. Let's take out our green highlighter, denoted as xi, I equals 1 to n. So each image is x, and then there's n total of these images, right? And they're indexed from 1 to n. You have a generative model P of X, so this is a neural net. The neural net is a function that takes in the image X and then produces a latent, I guess. Gaussian noise is progressively introduced into the source images at an arbitrary time step t. So your diffusion process is going to have t total time steps, capital T. You have a noise schedule, so when you're adding or removing noise, that function is dependent on the time step. So early on in the image, you're probably going to be more aggressively removing noise. And later on in the image, when you're closer to the final image, the amount of noise that you remove is probably less. So there is a schedule to the actual noise without iterative forward sampling. I don't know what iterative forward sampling is. Sampling, I guess, is the sampling of the noise, and then forward, I guess, is maybe the time step ahead of you, so some kind of technique based around sampling ahead. I don't know. Consequently, the noisy image at time step t, denoted as x of t, can be expressed as xt equals 1 minus alpha bar t x naught plus alpha bar t epsilon t here. So this is your noise schedule here. So image at time step t is basically the image at time step x naught plus however many alpha bar t here. You can see it as the product. So this giant pi from I equals 1 to t, what this means is that it's alpha 0 times alpha 1 times alpha 2 times alpha 3 all the way to alpha t. So you're basically multiplying those together. It's like a summation, but a multiplication instead. Cumulative product, I think it's actually called. But the image at time step t is basically you cumulatively add this noise. X naught represents the source image, while here you have the actual Gaussian noise. So this fancy script n means a Gaussian, aka a normal distribution. The 0 here means that the distribution is centered on 0, right? So that the big hump of the bell curve is right on 0. And then the I means that it's the variance or the standard deviation is 1, which means that it's exactly the shape that you would expect, right? Gaussian distribution. There you go. That's what it is. Centered on 0. With an STD of 1. Okay, in the reverse process, a denoising neural network, so you have your generative model P of X, and then you have your denoising neural network D theta of dot. Theta is the actual parameter, so in this case it would be 3 billion parameters. Is employed to estimate the additive Gaussian noise. The optimization of this network is achieved by minimizing the loss function. They really should have made this a separate paragraph. This is kind of weird to make it in line. But the loss function that you're trying to solve is you're trying to say that the expected value given some time step t, given some original image x naught, given some noise sampled from this Gaussian, you're trying to say that this denoising neural network which takes the image x of t at the time step, this denoising neural network is going to basically say, here's what the noise was. I'm going to remove this, aka this is the noise, right? So it's trying to predict that noise, and that noise should ideally match the actual noise that you added, and the difference between those, and the L2 difference specifically. So whenever you see these 2s here, that means they're doing the squared difference. And the reason people do the squared difference is so that the further away these things get, the more and more intense the error gets, right? It increases quadratically with the distance from the target and the prediction. And that's the basic denoising loss. By employing Bayes' theorem, it is feasible to iteratively estimate the image at time step t minus 1 through sampling from the posterior distribution p theta xt minus 1 given xt. So the distribution of what the image after a time step looks like. Posterior just means after. Prior distribution, posterior distribution is prior is the before, posterior is the after. We have xt minus 1 over alpha bar, or not, this is just alpha t times xt minus 1 minus alpha t, 1 minus alpha t bar squared d theta. So all they did was they took this equation here, this xt, and then they just plugged it in. And now you have the actual xt with the noise coming from this denoiser, right? So here, they use sigma t right here, right? And because this denoiser function should ideally basically approximate this value, you can basically take this and plug it in there. Okay, and now they introduce this new little thing here. Sigma t signifies the standard deviation of the newly injected noise into the image at each time step. Z represents the Gaussian noise. Okay. So this is the reparameterization trick. I think they pull out the pure Gaussian noise here. I don't know. It's a little weird. In essence, the denoising neural network estimates the score function at varying time steps, thereby progressively recovering the structure of the image distribution. The fundamental insight provided by the DTPM lies in the fact that perturbation of data points with noise serves to populate regions of low data density, ultimately enhancing the accuracy of the estimated scores. Okay, so what are they saying here? The perturbation of data points with noise. So the fact that you're taking images and adding noise, right? This is confusing because I think what they're referring to here, data points, they're not actually referring to specific points in the image. They're referring to the image itself as a point within a distribution of images, right? Serves to populate regions of low data density. So you have some distribution which represents all your images, and there's parts of that which have low data density, right? Maybe you just have one example of an image that kind of in that region of the image distribution. And if you take that image and then just add a little bit of noise, right, especially Gaussian noise, you're kind of like filling out that region of image space, or that region of the image distribution on image space, I guess. I don't know, that's my interpretation of that, but we'll leave it there. UNet with text prompts. The denoising network is commonly implemented using a UNet. So a UNet is a network that starts very wide and then goes very thin. There's kind of this choke point, and then it goes back to being wide. This was originally used for segmentation a lot. To incorporate textual prompts denoted by Y into the UNet, a text encoder neural network. So you're not going to condition your diffusion process on just raw text, right? You're going to tokenize that text, and then you're going to encode that text. So that's what this E of theta is. It's some kind of encoder for text, and the encoder for text itself probably requires a tokenized version of the text. The extracted text tokens are input to the UNet through a cross-attention layer. The text tokens possess a size of ny times dy, where ny represents the number of text tokens and dy signifies the dimension of the text token. Okay, so 768. Okay, so here is where you actually have the cross attention, right? You have a furry bear under the sky. This is the text. That text is somehow encoded before, so they're missing a block here. This text should be encoded. There should be a network here that encodes the text. All right, wait up. Let's read this figure 3 and then see what the fuck these figures are. Each block contains 4 primary components, including a self-attention layer, a cross-attention layer, and a space MOE layer, and a time MOE layer. The space MOE is responsible for depicting different text concepts in specific image regions, while the time MOE handles different diffusion time steps. Each block uses edge-supervised cross-attention learning. The fuck is edge-supervised? To further improve image quality. For example, given a prompt, each text token and its corresponding image region, given by binary mask, are directed through distinct space experts. Okay. So at least we're learning something here. So this right here, corresponding image region given by a binary mask. So before when I was reading this paper, I thought that the image region would have actually been just cutting the image up into these little patches, similar to what a vision transformer does, but that's not what they're doing. When they refer to an image region, what they're referring to is basically a mask. So there's going to be these masks, and then the different image regions are going to be defined by these masks. And it looks like they're getting these masks from the attention map. Each expert learns particular visual features by stacking. We can easily learn to depict thousands of text concepts. Okay. I see what's going on here. Okay, so you have your text tokens, right? And you also have your image tokens. And you have cross-attention between your text tokens and your image tokens. That cross-attention is going to give you an attention map, right? So this sequence of text tokens and this sequence of image tokens, right? Image patch tokens is going to result in this attention map that's going to say this part of the image has a higher attention, right? Whenever you multiply the little image token and the little text token, sometimes that little dot product is going to result in a big number, which means that that's what the bright value in this attention map is, right? So this means that the little dot product between the text token and the image token, or I don't exactly know where they're getting this image token from, but high agreement, bright value, low agreement, low attention, dark value. So to me, it makes the most sense here, right? The word furry and the word bear, they kind of have high attention with this part of the image here that represents the actual bear, right? Versus the word sky, it's going to not have a lot of activation or attention or whatever you want to call this with the bear itself. It's only going to really have it for the background. So then they're going to threshold this. So they have some human-defined threshold for how bright does it need to be in the attention map for us to create this mask. They're going to create this mask. I don't know what this freeze and this fire is. Usually this means that they probably freeze. Like usually when you see this, it means frozen, but this is usually in the context of fine tuning. Like you'll freeze parts of the model when you fine tune. So I don't know what this means in this context. But this gets fed into expert 1, expert 2, and expert n total experts. This is a really poorly designed diagram. This is the edge loss. So they say edge supervised cross-attention learning. So there's some kind of supervision happening with the edge. So L edge. The output of the time mixture of experts goes into the space mixture of experts. Dude, what the fuck is this thing? I want to be honest. I don't know what this figure is trying to tell me. It's like it's just not, it doesn't make things clear. It just makes things more muddy. Okay. Let's see if we can read more of this and then maybe we'll understand it better here. The cross-attention layer can be formulated as an attention mechanism. This is just your standard attention mechanism in a transformer. You have your queries, you have your keys, and you have your values. Your keys and your values multiply with each other. You divide them by, holy shit, the square root of d, which I think is the dimension of that. And then you multiply by the values. The way that I like the way that Karpathy explained these, where the queries are the things that I want, keys are the things that I have, and then V are the things that I'm looking to communicate. That's the way that he describes it. So the things that I want and the things that I have, you multiply those together, that's where you get the high agreement. And then the values are the things that I'm going to communicate to the next layer. These matrices are computed as QHXT times, this is the actual weights, right? So these are the actual weight matrices here, W, Q, W, Y. Oh my God, I hate it when the LaTeX isn't nice. And then W, val, Y, where W, query, X, this is the dimensionality of the query matrix. This is the dimensionality of the key and the value matrices. Represent the parametric projection matrices for the image and text. D denotes the dimension of the image token. Okay, so they reference image token here, so that kind of confirms. They never mentioned image token here, so I was a little bit confused with this cross attention, but as soon as they say image token, so now that kind of confirms what we were predicting here, that there is some cross attention here between the image tokens and the text tokens. So this text here is first tokenized and encoded, and then each word in there is going to have a corresponding text token. And when you're going to take your image, you're going to probably encode it into a sequence of image tokens. And then the cross attention is going to be between the text tokens and the image tokens. So each image token is this HXT, where D is the dimension of the image token, right? So how big that vector is, which I think it's 760, or no, this is the text token is 768. So each text token is one vector of size 768. And what is NX? NX is the number of tokens in an image. Okay, so a vision transformer, a VIT16, right? So here is a VIT, I guess, 3x3. So in this, if you cut up an image into this 3x3 grid, you end up with 9 possible tokens, but generally common sizes are 16. And I think I've also seen VIT 32. So that's the number of tokens in these vision transformers. Cross-attention map between the texts and the image is defined, which plays a crucial role in the proposed approach as described in the following section. So if you've been inside this deep learning world, you know of the fact that attention mechanisms, specifically the transformer attention mechanism, is quadratic with respect to the length of the sequence, right? So in a attention mechanism for text, you have the sequence self-attentioning with itself, right? So you would have ny cross ny would be the dimension of that, right? Quadratic with respect to ny. But here, this is not self-attention, this is cross-attention. So now the total memory footprint and compute footprint of this cross-attention is now basically the size of, or the number of your image tokens, aka the length of your image sequence, times the number of text tokens, aka the length of the text sequence. So you still have this quadratic relationship, except now it's not quadratic with respect to itself, kind of, right? Because of the self-attention. Now it's quadratic with respect to two different things. It's the size of the text, or the length of the text, and also the length of the image. They never explain how the image tokens are generated. I presume it's from the UNet feature maps, but in the outer layers of the UNet, they probably need tiling. Yeah, I mean, so far they haven't told us what they're using to encode the text. They haven't even told us what they're using to encode the image. But using the word image token, to me, that just screams VIT. Like, as soon as I see image token, I think vision transformer. So my guess is they're probably just using one of the vision transformers on ImageNet or on Hugging Face. They're super popular too. If you actually go to Hugging Face, view all docs, and you go to models, and then you sort the models by most downloaded. The most downloaded models are these giant pre-trained vision transformers. So this VIT16 Dino out of Facebook, which is the self-supervised one. This is what I would guess they used, right? But even this, right, it only goes to 224 by 224. How many tokens does this have? VITB16. Let's actually go to this paper. Network configuration, employing a UNet. The framework consists of 16 transformer blocks, each containing 4 components: a self-attention layer, a cross-attention layer, a space MOE layer, and a time MOE layer. So this is the VIT16. See if we can get an actual picture so we can see exactly how it chunks the image. We do not get a picture. Well, that's lame. Control F, tokens. Okay, so actually here you go, boom. So a VIT-B16 has 197 tokens. So compare that to how many tokens there are. A furry bear under the sky, that's probably something like 10 tokens at most. So it's like 10-ish tokens. And then your image is going to have something on the order of 100 tokens, probably 1,000 tokens at most. So it's like order of magnitude calculation here. You have 100 something tokens for the VITB and then 10 tokens for the text. They have 16 individual transformer blocks within a UNet, maybe 8 on the left and 8 on the right. Maybe, we'll see. This paper isn't very well written. It's a little bit confusing, to be honest. Regarding the space MOE layer, distinct text tokens correspond to various regions within an image, as previously mentioned. When provided with a prompt, furry bear, the text token and its corresponding image region, represented by a binary mask, are fed into separate experts. The space MOE layer's output is the mean of all experts, calculated using the following formula. Okay, so we get a little bit more information here on what the space MOE is. So the space is the mean of all the experts. calculated using this formula. 1 over ny, where ny is, I think they defined it up here, ny is the number of text tokens. So they're normalizing with respect to the total number of text tokens. And that makes sense because each text token, right? So there's going to be a mixture of, or there's going to be a space MOE for each text token. So whenever you take the average or the mean, which is what they're saying here, you're going to have to divide by the total number of text tokens, right? And depending on your prompt, you're going to have a different number of text tokens, right? So here in the text tokens for this prompt is going to be higher than the text tokens for this prompt, right? You're going to have a different number of text tokens here than you're going to have here. So they're dividing by that. They're summing up all of them. E-route, I don't know what this is. I think this is probably the encoder, whatever this is. E-route is probably the text encoder here. Text encoder neural network, E-theta. And then yi is the actual text token before it's encoded. H bar or H prime of xt times mi hat. This is element wise multiply, I'm pretty sure. Let me make sure of that element wise matrix multiply symbol. Yeah, yeah, it is. Okay, so I just wanted to confirm, but basically that empty circle like that means that it's element multiplication. MI is a binary two-dimensional matrix. Okay, so this is the mask, indicating the image region in the ith text token should correspond to. Okay, so basically they're using the image mask to mask out any part of this attention that is not related to the specific token. So they have a different expert for each text token, and then however many of these experts, which is going to depend on the number of tokens in the text. So they're going to have a different number of experts constantly. Every single image is going to have every single prompt is going to have a different number of experts. And all they're doing is they're basically zeroing out everything so that the only thing that matters is what's inside this mask. But there's going to be some threshold, right? This is a binary mask. So at some point you have to say, okay, everything below 0.5 is going to be 0 and everything above 0.5 is going to be 1. So I don't know how they're deciding that. That seems like it would be very important. Indicating the image region in the ith text token should correspond to dot represents Hamard product. Okay, maybe I was wrong. Isn't Hamard product just another way of saying image what? Hamard product? Multiplied corresponding. Yeah, okay. It's just element-wise multiplication, but you know, I guess you gotta give this random ass dude Hamard this guy, Jack Hamard, dude. He came up with the element-wise multiplication. So forever now, we got to make sure to always give him credit and call this the Hamard product instead of just element-wise multiplication. H bar xt is the features from time MOE. Okay, so here, features from time MOE. E and E are different. Capital E is the text encoder. Lowercase e is the expert feed-forward neural network. The gating routing function returns the index of an expert in the same MOE, with e to the 1 to e to the k being a set of experts. So you have k total experts. You have a routing. So routing generally refers to basically creating this kind of like one-to-one mapping, being like this corresponds to this, this corresponds to this, this corresponds to this. So they're doing some kind of routing here and saying, okay, you have to basically map between a specific time expert and a specific space expert. You know what? Here's another. Have you guys ever heard of this? Capsule networks? Capsule networks had this kind of routing mechanism as well. Yeah, they called it routing by agreement. Or the outputs of one capsule are routed to capsules in the next player according to the child's ability to predict the outputs. Dynamic routing mechanism. So maybe this is kind of where the inspiration is coming from. You can kind of think of each expert as kind of like a capsule. I don't know. What do you say, Nisio here? I actually think when they say expert n in the diagram, they mean the value k from 1 to 6 for e to the k. There's always 6 space experts in the experiment. Each text token is fed to separate experts. The space MOE's layer output is the mean of all experts. Okay, so they do have the same amount of experts all the time, and then you have some routing. Like, even just the little things kind of annoy me here, right? So they say a set of K experts, and then here they have expert N, right? Like, why not just call it expert K if you're going to use this K? The text gate network is employed to distribute an image region to a specific expert, aka route a specific image region to a specific expert. The function route, yi, argmax, softmax. So argmax here means that they're picking the one that has the highest value. So softmax turns it into, this is kind of what happens whenever you're doing classification. In classification, you're taking your logits, which is the last layer, you're doing the softmax, and then you're picking the argmax out of those. So this is kind of a similar operation here. Let's see. Classification model head. See if I can find a good pick. No, all these picks suck. I'm losing it, guys. All right. So we got this function route yi here, which is what they're using here, route yi. They're adding noise to that. G is a feed forward network. So this here is a network which maps from the space of dy, which is the dimension of the text token, into k, which is the dimension of the experts. Okay. So this is why, and this function g is why there's a different number of experts than there are text tokens, because you have something that maps it to this same size, or else you would have a different, or else the number of experts would be the number of text tokens, but because they have this feed forward network here that maps from whatever dy is into k. No. I'm just confusing the shit out of you guys today. dy is not the number of text tokens, it's the dimension of the text tokens, which uses a text token representation, e theta yi. So this is the actual function that returns text tokens as input and assigns a space expert. Okay, so you have this function g, which is a network, it's just a feed forward network, and it takes in all the text tokens, and basically you go through that network, you're going to get a bunch of values, you're going to take the softmax of all those values, you're going to add a little bit of noise, this noise here, and then you're going to say which one of these has the highest value. That's what the argmax does, and then that's going to tell you the index of the expert that you're going to use. To prevent mode collapse, random noise E is incorporated. The argmax function ensures that one expert exclusively handles the corresponding image region for each text token without increasing computational complexity. I just don't like the use of the word image region here, because that to me means like one local patch. I would use masked image. And that also kind of shows why this website is so trash. This also shows why you get the behavior here. So you note how one of the things that stands out with this comparison here is that the background is always generally good, right? They're saying flower, knight, sword, like the flower's in the background. So the actual center of the image, right, the object of this actual person here, that seems about the same between the Stable Diffusion and the RAPHAEL, but RAPHAEL is very good at the background. You see that? How the background is always pretty good? And I think the reason the background is pretty good is because it's all based around this kind of idea of these masks. So that's why it's able to get pretty good backgrounds. Very confusing paper. Yeah, it's like they're not really trying to explain this very, very well. It's almost like they're trying to obfuscate what they did. We visualize the diffusion paths routes from the network input to the output, utilizing 16 space MOE layers, so 16 total of these space experts, 16 layers, each containing 6 experts. Okay. 16 total layers, each of them with 16 experts, or 6 experts. These paths are closely associated with 100 adjectives, which represent the most frequently occurring adjectives for describing artworks as suggested. Okay, so at each layer, right, they're doing this routing. So at each layer, they're only going to feed the input or the output from one layer into the next layer is only going to be done through one of the experts, right? Because of this argmax here. Because of this argmax, you're not going to take this input and give it to the rest of the experts here. You're only going to give it to one of them. So that's why there's basically only one connection at each subsequent layer here. And one thing that I don't get here is I feel like you would assume that these experts correspond to specific semantic concepts. You know, even just something like background, foreground, or something like that. But like, what does it mean that banana starts here at expert 0, and then it goes down to expert 4, and then it goes to expert 2, and then it goes to expert 0, and then it goes back to expert 1? Like, what am I supposed to intuit from that? Given that GPT 3.5 is trained on trillions of tokens, we believe that these adjectives reflect a diverse real-world distribution. Our findings indicate that different paths distinctively represent various adjectives. Different paths represent different adjectives. That seems like kind of a stretch. I don't know what the fuck that's supposed to... So what they're saying is that somehow a specific sequence of experts, right? So going from expert 0, then 3, then 5, then 2, then 4, then 1, then 3, somehow that's supposed to represent a concept like peaceful. I don't know if I agree with that, right? Because it's like, if each expert is basically just a mask, right? The concepts that it's representing are more like background, foreground. So we depict the diffusion paths for 10 categories within the COCO, reveal that different categories activate distinct paths in a heterogeneous manner. Like, just look at this figure, dude. Like, what the fuck is this? This is the world's shittiest figure. I can't even read this. Like, what does this mean? All right. From text to image region. Maybe they mean each expert is slightly different, not all the same, so it will judge differently. I gathered the 16 space MOE layers are completely independent, like different neural nets completely, all initialized differently. Yeah, I'm guessing they're probably training this from scratch. This is like weird enough that they're training this routing thing from scratch. Recall that M is the cross-attention map between text and image. Okay, I agree with that. But that's honestly not a very good choice because M... So M here, star, comma 1. This is the cross-attention map between image and text, and then M hat is the mask. Yeah, M hat is a binary two-dimensional matrix. This is the mask, and then M is the cross-attention map, where each element MJI represents a correspondence value between the jth image token and the ith text token. Okay, that all makes sense. In the space MOE, each entry in the binary mask equals 1. Okay, so here we finally get this magic threshold that I was talking about. So what is this magic threshold? Okay, so this magic threshold is actually the result of a thresholding mechanism is introduced to determine the values in the mask. The threshold value alpha max M star I is defined where max M star I represents the maximum correspondence between text token I and all image regions. Okay, so the threshold changes depending on the text token. So here they said that in this cross-attention map, right, you're going to have I is the kind of indexing for the text tokens, and then J is the indexing for the image tokens. So for all image tokens, so one text token and then all image tokens, so basically like one row, you're going to find the maximum activation. Here they're calling it correspondence. And then that maximum activation is going to determine what the threshold is. So I guess that kind of, I kind of like that, you know, because they could have just said, okay, the threshold is this hyperparameter alpha, right? So they could have just said, hey, we're just going to pick some random alpha, and then that's going to be the threshold for this mask. But instead of that, they said, hey, for each individual attention map, we're basically going to say this word or this image token, or sorry, this text token, we're going to do the entire cross attention to every single image token, and then we're going to basically take the maximum activation, and then the alpha is with respect to that maximum activation. So it's kind of like they're normalizing based on the activations there, or correspondence. Okay, I kind of like that. I like this little trick that they did there. The insight behind the space MOE is to effectively model the intricate relationships between text tokens and their corresponding regions in the image, accurately reflecting concepts in the generated images. The employment of 16 space MOE layers, each containing 6 experts, results in billions of spatial diffusion paths, 6 to the 16 possible routes. So here they're basically saying each of these, you have 16 layers, and then you have 6 different possible experts, and route is like one specific path through here. So if you calculate that all out, you have billions of possible different paths. It is evident that each diffusion path is closely associated with a specific textual concept. This is the part that I don't know if I agree with that. I feel like that's not super easy to intuit, but hey, if they can kind of visualize things in 20 dimensions and they think that it's obvious, maybe it is. We generate 100 prevalent adjectives that are the most frequently occurring adjectives for describing artworks as suggested by GPT 3.5. So they ask GPT 3.5, what are the most common adjectives? Okay, prompt templates, generate 100 distinct images. By treating these pathways as features, each path is a vector of 16 entries. Okay, that's one way to think about it. We train a straightforward classifier to categorize these words. Oh, this is kind of cool. The classifier, after 5-fold cross-validation, achieves over 93% accuracy for open-world objectives. Oh, shit. Okay, so actually now I agree with them. So it is not evident that each diffusion path is associated with a specific textual concept, but if you train a classification model on the path, right, they're saying each path, they're going to represent a vector. So the word airplane is going to have a specific path, right? There's going to be a vector with 16 numbers, each of those numbers representing which expert it took at each layer. And then they're going to pretend that that's some kind of feature. And then they're going to use that feature or the route, and they're going to say, okay, can you train a classifier that given the route predicts the word? And it does with 93% accuracy. So that is pretty cool. We observe analogous phenomena within 80 object categories of the COCO dataset. Okay, so COCO, obviously, mostly it's a classification dataset. So they took 80 of the categories from the COCO dataset, which are probably things like airplane, cat, dog, human, chair. And they also found that you could train a classifier given the route to predict the category. That's kind of cool. All right, time MOE. Well, I'm not sure why they wouldn't use a frequency list of 100 most common adjectives instead of giving GPT 3.5 to give you a list. Yeah, and it's also weird because GPT 3.5 was trained up until September 2021 or something like that, right? So I'm pretty sure that Stable Diffusion was after GPT 3.5 was trained, which means that GPT 3.5 is not aware of basically what Stable Diffusion is and like that whole explosion of text to image generation, right? I think about how much more forums and Reddit threads and kind of just tokens have been created that are talking about image generation, talking about the best words to use for image generation, talking about which words work well and which words don't work well. So to me, GPT 3.5 was trained before that happened. So I just feel like it's not going to be as good as something that's trained with all the Reddit threads and all the Discord chats and all the crap that has happened up until then, right? Somebody should do that. Somebody should take the Midjourney Discord. So Midjourney has a Discord where people sit there and they talk about the best prompts to use. Somebody should just fine-tune a model on that, and I bet you that model would be significantly better at picking words, right? Compared to what they did here, where they just got GPT 3.5 to just pick 100 words. Okay. Time MOE. Given that the diffusion process iteratively corrupts an image with Gaussian noise over a series of time steps. It's a good definition of diffusion models. The image generator is trained to denoise the images in reverse order. Yeah, so whenever you're training, you add noise. Whenever you're performing inference, you remove the noise. All the time steps aim to denoise a noisy image, progressively transforming random noise into an artistic image. Intuitively, the difficulty of the denoising steps depends on the noise ratio presented in the image. Whenever t equals t, the denoising network's input image is highly noisy. When t equals 1, the image is closer to the original image. Yeah, so that's why you have a noise schedule, is so that you can alter the amount of noise that is being removed depending on the time step. To address this issue, we employ a time MOE before each space MOE in each transformer block. In contrast to this other work here, which necessitate handcrafted time expert assignments, we implement an additional gate network to automatically learn to assign different time steps to various time experts. Okay, so I think this reference here is their own work. Right, so if we click on that, text-to-image diffusion models with an ensemble of experts. Okay, so there seems to be basically this entire kind of literature on this kind of mixture of experts specifically for text-to-image diffusion, right? You have a 2022 paper here with ensemble of expert denoisers. You have another 2022 paper here, which I think is the one that they referenced before, with a mixture of denoising experts. So there's basically, this isn't original in the in the use of a mixture of experts or a bunch of experts. So that's important to realize, is that they're just building on previous work here. But some of these previous works had handcrafted time expert assignments, and here they're basically going to learn a gate network. So they're going to have an additional little neural net that assigns different time steps to various time experts. So very similar to what they were doing with the space experts, where you have a little network, a little feed-forward network here that is routing into a specific space expert. They're going to have a similar kind of thing where they have a little neural network that routes it to a specific time expert, although they don't use the word route here. So in order to further enhance the image quality, we propose incorporating an edge supervised learning strategy to train the transformer blocks. Okay, so what the fuck is this? Edge supervised learning strategy. So supervision occurring with edges. By implementing an edge... Okay, this is ControlNet. All right. Okay, so edge detection module. Let's go to our ControlNet image. Let's actually go to the original ControlNet. ControlNet? Yeah, right here. So in ControlNet, right, you're training, you're freezing your neural net, you're freezing your stable diffusion, and you're kind of creating this. So it's kind of similar to a LoRa, but it's not actually a LoRa, right? But you're adding this additional kind of little mini parasitic network that attaches to your frozen pre-trained network. And this little mini parasitic network is given a specific control thing, right? And the thing can be a lot of different things. They call it here a condition, but it can be an edge, right? So this is what an edge map looks like. An edge map, there's a lot of different ways to get the edges on things. There's canny edge detection, but then there's also probably neural network-based methods to get edges. They're probably using the canny edge detection, would be my guess. But they're doing the same thing here as ControlNet, where they're basically adding that additional supervision coming from an edge detection version of the image. These intricate boundaries can serve as supervision to guide the model in preserving detailed image features across various styles. Consider a neural network module P theta M. Okay, so you have a new neural network here, P of theta, with parameters of n convolutional layers. I don't like the fact that they're reusing the n here. Module is designed to predict an edge map given an attention map M. Okay, so they're not using canny edge detection. They have a different neural net which is specifically predicts an edge map given the attention map. Okay, so they have a neural net that takes the attention map, this little thing here, and produces an edge map, which is going to look something like this, right? It's going to be similar to a mask, that it's only going to have values of 0 and 1. But the 0 and 1 are not going to be like kind of one blob. It's going to be like basically an edge. We utilize the edge map of the input image, denoted as I-edge, to supervise the network. Okay, so they do use canny edge detection. They use canny edge detection, probably, I don't actually know, but they use something like canny edge detection to get the edge of the actual input image, right? That's going to be the ground truth edge, if you want to think of it that way. And then they train this neural network P theta in a supervised learning manner to basically map this I edge. Okay? And why are they doing this, right? Why the fuck do they have this extra step where they train a edge detector that specifically works on the attention map? And the reason they're doing that is because you don't have the actual image in inference, right? So when you're doing training, right, you have the original image. So you know what the original image is. So you could just say, hey, what's the edges for the original image? Here it is. Okay, boom, we're good. Let's use those edges. But when you're generating an image in inference mode like this, that image is, you don't know what the image is until you generate it. So how are you going to get the edges for an image that you don't know yet? So that's why they had to train this additional neural net here that will give you the image by looking at the attention map, because you don't have the final image, but you do have the attention map. iEdge can be obtained by holistically nested edge detection algorithm. So this is the actual edge detection, is not canny edge detection. Maybe it's canny edge detection. I don't know what holistically nested edge detection is. Intuitively, the network P of theta can be trained by minimizing the loss function. Focal loss between the edge ground truth, which is coming from your input image, and then the output of your neural network, which is trying to give you the edge image, but using the attention map as input. So the difference between those, focal loss. Focal loss is a different loss that basically also does the same thing. It's like determines the distance between two images. Employed to measure the discrepancy between the predicted and the ground truth edge maps, where the ground truth edge maps are iEdge, and then the predicted edge map is this P theta M. The attention map is prone to becoming vague when the time step t is large. Consequently, it is essential to adopt a time step threshold value to inactivate pause edge supervised learning when t is large. This time step threshold value is a hyperparameter that will be evaluated. Okay, so I keep fucking up the colors here. But there's an additional hyperparameter here that they're going to have to pick that is basically going to be at what point is the difference between, or is the time step that you take when you're doing this denoising too big? Because if the time step is too big, then the attention map, which is the input to your edge detection network here, this P theta, becomes too vague. I don't know what vague means in the context of an attention map. Overall, the RAPHAEL model is trained by combining two loss functions, L, denoise, and edge, as demonstrated. Okay, so your denoise is your main loss, right? You want to be able to just predict the noise. And then your edge is this extra edge loss. Edge supervised learning substantially improves the image quality and aesthetic appeal of the generated images. So, I mean, I don't know if I've ever seen this before, this like weird like edge map given from the edge map predicted from an attention map used as an additional supervision, use an additional loss for a diffusion model. So if this is the biggest contributor to their performance, this might actually just be the biggest thing to take out of this paper, is that you want to use this edge supervised learning. But this just seems like so annoying and complicated that I don't know. Right? This is starting to look like one of those systems that has like 500 different like things that are all feeding into one another, and it's like, do you get to a point with a system where it's too complicated to reasonably use? Is the intuition for this something like they're encouraging the text and image features to contain enough information within 5 conv layers that can be used to guess edges? Yeah, I think it's just they're right, when you have this P theta of M, right, this neural network that predicts the edge map given the attention map, it's probably looking at basically these boundaries. So I think what this edge signal does is it makes these boundaries here more kind of like crispy, and the crispier these boundaries are, the easier it's going to be to threshold whenever you're doing this mask. So I think to me that's the point, is that these masks need to be very clean in order for their whole mixture of experts to work. So by adding that edge supervision, they're making sure that these edges are crispy, which means that you can get better mask, which means that their space MOE works better. That's my guess. Experiments. Section contains experimental setups compared to the recent state-of-the-art models in the ablation study to demonstrate the effectiveness. More artistic images and comparisons can be found. The training dataset consists of Leon 5B and some internal datasets. To collect training data, we filter images using the aesthetic score, same as Stable Diffusion. Okay, so this is kind of interesting. Leon 5B, Stable Diffusion filters it with this aesthetic scorer. So that's kind of interesting, where basically you don't want to train on every single image in Leon 5B. You want to filter it and remove the images that are weird and images with watermarks and stuff like that. Text descriptions in Leon 5B are noisy. We clean them by removing useless information such as URLs, HTML tags, and email addresses. Is that useless information? I don't know. Multi-skill training. To improve text-image alignment, instead of cropping images to a fixed scale, we resize an image to its nearest size in a bucket, which has 9 different image scales. Resize an image. So, in a lot of computer vision pipelines, right, you end up using pre-trained image models that have a specific input size, right, such as 224 by 224. But in these huge data sets like Leon 5B that are scraped from the internet, not all your images are going to be the same basically size or ratio, if you want to think of that. You're going to have wide images, you're going to have tall images. So you need to basically put them into a square. You need to make them that square crop, that 224 by 224 or 128 by 128, whatever it is. So sometimes people do that by cropping, right? But another way you can actually do that is by resizing. The problem with the resize is that then you can warp the images, so you can actually like make them kind of too thick or too tall, and it warps the actual content of the image. So sometimes people resize and then they pad, so then you'll have these like kind of black bars in the image. GPU resources will be automatically allocated to each bucket depending on the number of images it contains, enabling effective use of computational resources. What do they mean by bucket? They're doing it at different scales? That's weird. I mean, at some point, it's getting converted into image tokens, and those image tokens are all going to be of the same dimension. So you have different conversions for different sizes. So you have 9 different image encoders, is basically what I'm reading here. That seems really weird. Side note, in the last few days, Japan and Israel said they will allow AI models to train on copyright images. Yeah, I think that's good. You know, like, the only people who care about copyright are like people like Disney. You know, it's like Disney doesn't need any more money. You know, like copyright only really benefits like these big giant companies like Disney that have IP like Marvel and Mickey Mouse and crap like that. Like your average person isn't really benefiting from really strict copyright laws. So I don't know. To me, it's like a general purpose AI is useful for all of humanity. So make it easy and not illegal to train the biggest possible AI that you can, right? I think the benefit of humanity is more important than the amount of money in Mickey Mouse's bank account. Let's get a little bit more coffee in my system. To reduce training and sampling complexity, we use a variational autoencoder to compress images using a latent diffusion model. Okay, so this is the actual encoder that they're using to take the raw images and turn it into a image token. So let's actually see which one they use. Neural discrete representation learning. I think this is just the OG VAE paper. Yeah, both of these things that they reference, these are just like super high level. So I doubt they're actually using this exact, the VAE in this exact paper, because these are really old. This is 2017, 2019. They're probably using their own internal VAE that they trained at SenseTime. Yeah. We first pre-train an image encoder to transform an image from pixel space to latent space and an image decoder to convert it back. So I don't think this pre-training was done for this work. You know what I'm saying? Like, here's my theory. Here's my little conspiracy theory. SenseTime is huge. SenseTime is one of the biggest computer vision companies in China, right? And I bet you they have their own image encoder, right? They've spent a ton of money and trained their own image encoder that they use for whatever purpose and reasons. And when you're sitting there and you're a researcher at SenseTime, you're like, hey, what image encoder should we use? And they're like, hey, well, actually, we have this really good image encoder that we trained and that we use for all of our other products. We should just use that for this research. So the fact that they referenced like really simple and older papers for a VAE, and the fact that they say, oh, they just give you like a one throwaway sentence here where they say, oh, we have an image encoder that's based on VAEs, and then they stop there, I think that to me means they're using their proprietary image encoder for this. Or the one in the reference. High resolution image synthesis with latent diffusion models. Do you think this is the one they use? Is my conspiracy theory dead on arrival? So which one do they use here? Model Zoo. Maybe they use this one. Yeah, maybe you're right, Nisio. Maybe they're not using some kind of super secret VAE. Maybe they're just using the VAE from that. Okay. Unlike previous works, the cross-attention layers are augmented with space MOE and time MOE layers. The entire model is implemented in PyTorch and is trained with the AtomW optimizer, with a learning rate of 1e to the negative 4, a weight decay of 0. Okay, so no weight decay. And then a batch size of 2,000. So, yeah, that's these monster batch sizes. You can really only get that on huge parallel training rigs, which that's what they did, 1,000 NVIDIA A100s. Following previous work, we evaluated RAPHAEL on Coco datasets using zero-shot Fréchet inception distance, which measures the quality and diversity of images. 30,000 images are randomly selected from the validation set for evaluation, shows that RAPHAEL achieves a new state-of-the-art performance on text-to-image generation with a 6.61 zero-shot FID 30K on MS Coco. Microsoft Coco FID 30K refers to the 30,000 images. Zero shot refers to that the model has not been fine-tuned in any way on the Coco afterwards, right? So this model is just trained on Leon 5B, so as far as I know, it's never seen Coco. I don't know if Leon 5B includes Coco. I don't know if anybody's done that. If they've looked at the images in Coco and they've looked at the images in Leon 5B and they've confirmed that there is no overlap. There might even be a little bit of overlap, if I had to guess. With the recent representative text-image generation models on MS Coco 256, outperforms all previous work. So here you have different work. Here we go, Stable Diffusion and DALL-E 2. These are probably the ones that are worth comparing to here. you have zero shot FID 10.39, and Stable Diffusion gets 8.32, and then RAPHAEL gets 6.61. Okay. So again, I feel like I always have a little section on this whenever I do these paper reviews, but to me, it's like benchmarks aren't perfect. And in these papers, there's a lot of pressure to get state of the art, especially when you're going to burn as many GPUs as they did, right? 1,000 GPUs. So they probably spent a bunch of time trying to figure out the one benchmark where they perform very well on, right? And they're sitting here pretending that zero shot FID 30K on MS Coco is like somehow this like God sent benchmark that is the perfect way to determine whether or not image generation models are better than the other, but it's probably not the case. And I'm sure the Stable Diffusion people can find some other random benchmark where their model is going to be the best. And I'm sure whenever whenever OpenAI releases DALL-E 3, they'll find some other random benchmark where they're the best. So I don't think there's anything sacred about this zero shot FID 30K. It just happens to be the one that they picked that had that made their model look good. We report the user preference rates with 95% confidence interval. This is more important. So user study, now I'm interested. So compared RAPHAEL to DALL-E 2, RAPHAEL to Stable Diffusion XL, this is more impressive to me. So they sat people in front of these pictures and they're like, which picture is better, A or B or C? A or B? And then just like a person sits there and clicks the one that they think is better. And the fact that you consistently get the RAPHAEL being better, I think is these charts right here mean a lot more to me than this table right here, I guess is what I'm trying to say. A bilingual prompt set which enables systematically evaluate given various text prompts. Human artists are presented with two sets of images and a competitor. They are asked to compare these images from two aspects respectively. They don't mention whether or not these sets of images are cherry-picked, so that's a potential way they could kind of game the system. RAPHAEL surpasses all other models. RAPHAEL can be further extended by incorporating LoRa, control nets, and super resolution GANs. We present a comparison between RAPHAEL and Stable Diffusion using LoRa. RAPHAEL demonstrates superior robustness against overfitting compared to Stable Diffusion. So that's what they were showing here in their website that doesn't work well. We demonstrate RAPHAEL with a canny-based control net. Furthermore, by employing a tailor-made super resolution GAN, we can enhance the image resolution to 4096 by 6144. Ablation. We conduct a comprehensive assessment of each module within the RAPHAEL model utilizing the CLIP score to measure image-to-text alignment. CLIP is still getting used, guys. CLIP is text and image both projected into the same space, so you can do these kind of distance metrics between it. You can say how far away is this text from this image, how far away is this image from this image, how far away is this text from this text. Given the significance of classifier-free guidance weight in controlling image quality, we present ablation studies as trade-off curves between CLIP and FID scores across a range of guidance weights. Figure Sys B compares these curves for the complete RAPHAEL model and its variance without space MOE, edge supervised learning, and time MOE. Okay, so this is good. This system has so many different parts that I feel like it's important that they did an ablation study. So I'm glad that they did that. Okay, so they have the system with all the parts, and then they remove the edge supervision. They remove the time mixture of experts and the space mixture of experts. CLIP score as a function of FID 5K. That's a weird thing to compare. But actually, it looks like edge, time, and it looks like these three lines, the green, the blue, and the orange, which are basically with the space MOE, are all pretty similar. And then here, the space MOE is really where you get kind of the different behavior. Number of experts. So this is I think they had 6, but they also try a couple different number of experts. The y-axis here is simultaneously FID 5K and then steps per second. Dude, what? That is weird. You have 2 y-axes that are like completely different things. TC. What is TC? Selection of alpha and TC. TC is the total number of time steps. So 100 time steps versus 700 time steps. Presents the trade-off between FID and CLIP scores for the complete RAPHAEL model and its variance without space MOE, time MOE, and edge supervised learning. Visualizes the correlation between FID 5K and runtime complexity measured in terms of the numbers of DDIM steps for an image per second. So, I mean, this is very slow, right? Look at this. They have 300 steps, and you're talking like 5 steps per second. So we're talking 10 or hundreds of seconds to generate an image, which is quite slow. Interesting how Deep Floyd was much worse in quality in Figure 5 comparison, but its FID was very good in Table 1. So Deep Floyd in Figure 5. Figure 5, Deep Floyd. It's really, really good there. Yeah, I see what you're saying. The difference between, or at least according to this zero-shot FID 30K benchmark, Deep Floyd is pretty much there. But in Table 1, where's Table 1? In Figure 5. Yeah, actually, that's a good point, Nisio. So, like, I was just talking about how this benchmark here, it shouldn't actually be, you shouldn't take this literally, right? Because it's like, you don't exactly know. But on this benchmark, Deep Floyd seems like it's pretty much just as good as RAPHAEL, right? Like, look at this, 6.66 with 6.61. But then when you actually look at the human study, you know, it's actually pretty shit. Deep Floyd is garbage. Humans don't think the quality is pretty good at all compared to the difference in quality between SDXL and RAPHAEL here. So look at the difference between these two here and these two here, and then look at the difference between this here and this here, and then this here and this here. So yeah, just more fuel to the fire that metrics are bullshit. Substantially enhances clip score, optimal guidance weight, sampler shifts from 3 to 4. At the same guidance weight, space MOE considerably reduces the FID, resulting in a significant improvement in image quality. So the guidance weight can basically control how much the text is like influencing the diffusion. So I guess there's some relationship between the guidance weight and the alignment, and that's a trade-off too. You have to pick this. So the user of the final product has to pick which guidance weight they kind of want to use. Choice of alpha and TC. We observed that alpha 0.2 delivers the best performance. An appropriate threshold value for TC. So this is the alpha that determines the where is it? It's up here. Hyperparameter alpha is the threshold for the activation in the attention map between the text and the image tokens. So 0.2 is the value that they pick there. And TC is the threshold for the, I think, the edge supervised learning. Yeah. the time step threshold used for the edge supervised learning here. So those are the two different hyperparameters that they picked. Sorry for scrolling through this so quickly. So alpha 0.2 delivers the best performance, and then TC is 500, which is actually huge. This is really big. That means that you can do the edge supervision as long as your distance is between the time steps is less than 500 apart. As soon as you have more than 500 apart, you don't want to do this edge supervision. So this actually isn't the total number of time steps. This is the choice of TC. So really here what they're showing you is that the blue line only corresponds to this x-axis here, alpha, and the red line only corresponds to this TC here. So this is really confusing as a plot because you're basically plotting these. There is no, you can't, like, don't take this blue line and then go down. Like, this alpha of 0.4 does not in any way correspond to a TC of 500. It's basically two separate plots over top of each other. Really what they're trying to show you is that there's a U-shaped curve for both of these, that if your alpha is too small, it's not as good. If your alpha is right, if your alpha is 0.2, you get the best performance, and you have this similar kind of like U-shape for the TC, where if the TC is too small, you're not going to get as good performance as a medium TC, and if the TC is too high, you're not going to get as good performance. T is always 1,000, so the total amount of steps is 1,000, but TC is the difference between the number of steps that you use for the edge supervision. So if the distance between those steps is too big, you don't use the edge supervision. We employ 100 million training samples. Demonstrate that increasing the number of experts improves FID. However, adding space experts introduces additional computations with the computational complexity bounded by the total number of experts. Once all available experts have been deployed, the computational complexity ceases to grow. The right-hand side, we provide a runtime analysis of 40 input tokens. For instance, when the number of experts is 6, the inference speed decreases by 25%, but yields superior fidelity. So kind of what they're showing you here is that TC and alpha, these hyperparameters have a U-shaped kind of plot, which means that there's kind of a magic number in the middle that's actually the best. You don't want them to be too low, you don't want them to be too high. But the number of experts, which is also a hyperparameter, does not have that relationship. Technically, what they're trying to show you here is that you could just keep increasing the number of experts and you would get better and better and better performance. But the reason that you choose 6 experts is because if you increase the number of experts, you're going to make it more and more and more expensive computationally. So for alpha and TC, you're picking the one that actually leads to the best performance, but for the number of experts, you're picking the value that kind of balances the performance and the compute cost. We review related works in 2 perspectives: mixture of experts in text-to-image generation. More related works. The mixture of experts method partitions model parameters into distinct subsets, right? Basically, because of this argmax that they're doing, right? If they didn't have that argmax, then it wouldn't be this mixture of experts. You have to be zeroing out things in order to get this mixture of experts. The MOE paradigm finds applicability beyond language processing tasks, extending to visual models, and mixture of modality experts within multimodal transformers. Ooh, that's kind of cool. Mixture of modality experts, so splitting up on modality. It's kind of cool. When's this paper? This is a 2023 paper, Scaling Vision Language Models with a Sparse Mixture of Experts. Dude, there's like this whole secret like mixture of experts like research area is basically what I'm learning from this paper. Additionally, efforts are being made to accelerate the training or inference process Secondly, text-to-image generation is to synthesize images from natural language. Early approaches relied on generative adversarial networks. I mean, we've seen a couple GAN papers that are more recent, so I don't think GANs are completely dead yet. So early approaches, it might be other approaches, relied on generative adversarial networks. More recently, with the transformative success of transformers, I like this sentence, with the transformative success of transformers, models such as DALL-E, CogView, and Make a Scene have treated text-image generation as a sequence-to-sequence problem. Utilizing autoregressive transformers as generator and employing image and text tokens as input and output sequences. Yeah, so once you have these vision transformers, you can treat an image as a sequence of tokens. Recently, another research direction has focused on diffusion models by integrating visual textual conditioning within denoising steps like Stable Diffusion, DALL-E 2, eDiff-I, and ImageGen. The suitable choice for TC equals 500 and then T equals 1000. Safe to say they start using the edge loss mid-journey. Dude, it's pun day. Dude, Thursday is pun day. We got transformative success of transformers. We got they start using the image or the edge loss mid-journey. Dude, we're going crazy on the puns today. Paper introduces RAPHAEL, a novel text condition image diffusion model capable of generating highly artistic images using large-scale mixture of diffusion paths. We carefully designed space MOE and time MOE with an edge-supervised learning framework, enabling RAPHAEL to accurately portray text prompts, enhance the alignment between textual concepts and image regions, and produce images with superior aesthetic appeal. Comprehensive experiments demonstrate that RAPHAEL surpasses previous approaches. Additionally, RAPHAEL has been extended using LoRa, ControlNet, and SRGAN. Limitation, social impact is to use API to create images. They're talking up this RAPHAEL API. They probably want to release kind of a mid-journey-like product. That would be my guess. We solve this issue before releasing the API to the problem. Prompt filtering. This is kind of a contentious issue now in Midjourney, right? Like a bunch of, I feel like the Midjourney subreddit, they're like complaining that the filtering on the prompts is becoming like really aggressive, which I don't know. All right, let's get into this appendix. Okay, so here are the actual values. So T equals 1000. So this is the total amount of time steps. NY is the dy is the dimensionality of the text tokens. NY, I guess, is the number of text tokens. I'm not sure. I think this is because they project it into that. That's why they're able to say there's just one. Weight decay, learning rate, number of space experts, number of time experts. Warm-up steps, batch size, GPUs, transformer blocks, focal loss. Here's your actual text encoder. So it's OpenClip G14. So finally you get the actual text encoder. They're using GELU activations. And then for these networks that determine how to route into a specific expert, they use just a generic feed-forward network, aka just a neural net. So here's the attention map. Here's the edge map. And then here's the image. So again, they have a specific neural net that predicts the edge map given the attention map, and it's trained in a supervised way to match the edge map that comes out from taking the original image. And in the human evaluation where they asked people, hey, do you prefer image A or image B? They noticed that the images that had edge supervision were significantly more preferred by the humans. The time MOE is composed of a time gate network to distribute the features of a specific expert according to the time step. H prime xt, this is the image. HCXT, I don't know what HC is. HC is the features from cross attention module. So basically the attention map. So the UNet here, transformer, you start from the image of noise, and then you go to the actual image. This is confusing because there's no notion of time here. This step is happening over many time steps, whereas this makes it just seem like there's some kind of thing that goes from noise to image space, which is not the case. Each block contains 4 primary components. Dude, whoever made these figures, like, these figures are so bad. Time MOE. So given the time step, this kind of router here, this little feed forward network, is going to pick which features go to which expert. So we saw how the space MOE basically does a argmax after a softmax. I wonder if this does the same thing, whether it does a argmax. These little lines here, this kind of represents an electrical switch. Like inside an electrical kind of schema, you'll see this, and that represents like basically whether the line, like a switch is on or off. So that to me means they're zeroing out things. So it's either going to be 0 or it's going to be the signal goes through. They might pad the tokens to be constant. The diagram really confused me. I think there should be 16, not 2 transformer blocks, and they just didn't have any space. Yeah, there should be 16 of them. But I just don't like the fact that this UNet doesn't have any notion of time, right? It's like this is not... There's a diffusion process going on here where you're doing basically a bunch of time steps, but like here it just looks like it just goes straight from xt to x naught. And the same thing here, right? Like it just goes a furry bear under the sky into TextGate, but they're missing a piece here, right? There should be this this open clip G14, right? You're encoding that text, and then for each of those text tokens, then you're actually doing this attention map, this cross attention map. So maybe to be more specific, what I don't like about these figures is that they're not complete. They're basically missing nodes and edges. So it makes it confusing because it's like, to me, if you make a diagram like this, one of these like node and edge kind of like graph diagrams, you have to include all the pieces, because if you don't include all the pieces, it feeds like there's random things going to different things, and it doesn't actually work like that in practice. Each block contains 4 primary components. The space MOE is responsible for depicting different text concepts in specific image regions. So the space MOE is all about this cross-attention map with respect to individual text tokens, and then this binary mask. The time MOE is conditioned on the time step here. Each block uses edge-supervised cross-attention learning to further improve image quality. Given a prompt, the text token and its corresponding image region are directed through distinct space experts. Each expert learns particular visual features. For time MOE, an initial time step is provided, followed by the selection of an expert responsible for handling the visual features. The routes of the time MOE in the first transformer block. The first expert focuses on noisy images, while other experts handle images with low noise levels. 0, 0, 0, 2, 1, 3. So this is the route, right? So higher up in the image, or in this paper, right, there's a specific route that you take over there's 16 layers of transformers, 16 blocks of transformers, and for each one, they have 6 experts or 4 experts, different number of experts for space and time. And then there's a path that it takes through that. So for example here, banana goes 0, then 1, or 0, 4, 5, 0, 1, right? So 0, 4, 5, 0, 1, or whatever that is. That's the route or the path. And then here they're showing you this is the path, that one specific path that it takes here. So 0, 0, 0, 2, 1, 3. I don't know what I'm looking at here though. It's like the first expert focuses on noisy images. What? The gating function returns the index of an expert in the time MOE with a set being a set of NT experts. Okay, so you have a similar kind of thing happening, in the time. So we know that the space experts there's only one that's chosen, right? There's a specific path. There's this argmax here. And the same thing is happening with the time experts, where you're going to only one expert. You're only going to the argmax of the expert. But in the previous, for the space expert, right, the network that chooses which one to go to, right, the gate network, is conditioned on the attention map. But here, the time network, the time gate network that's picking which expert to go to, is only conditioned on the time step. Time embedding. This is the first time they talk about a time embedding. So you can have position embeddings. So you can represent the position of something, like a position embedding is very common in transformers. I assume that rather than just feeding in a raw time step, like a number from 0 to 1000 or a number from 0 to 1, they're embedding that to make a little vector that represents the time, but with a little bit more kind of like fluff around it. This is where they train the classifier on the route. Here are the attention maps for the word tokens and then the image. So obviously it makes sense that you're going to have the word bear corresponds to the part of the image that's the bear, and the word table corresponds to the part of the image that's the table. I don't know how to judge the quality of these images, to be honest. I like this. These little cats talking into microphones, and I like this picture of this like random dude with a cat there. That's fucking great. A photo of an athlete cat explaining its latest scandal at a press conference. Cool. And I think then afterwards they just kind of show you more and more examples. All right. So let's get back to it. Let's see. Can I summarize this paper? So, summary of this paper. We had, in this paper, we looked at RAPHAEL, which is a very large text-to-image model, which is basically like a Stable Diffusion or like a Midjourney. This one specifically comes out of basically SenseTime, which is a large Chinese computer vision company. Most of it is the same. It is a diffusion model, right? It is basically, it's learning how to add and remove noise, and it's trained on the same data set as Stable Diffusion, which is Leon 5B, or specifically a filtered version of that. They do a couple different tricks that are different. So the main thing that they're doing here is they're basically have this mixture of experts concept where in between the layers of the transformer blocks, they're basically filtering, right? And they're filtering the signal that goes to the next layer. And the way that they're filtering it is with two different little neural nets. So they have one little neural net that filters based on these masks, right? And it's filtering based on the attention map between the text tokens and the image tokens, right? Where the image tokens are coming from a VAE image encoder, and then the text tokens are coming from a I think an open clip image or text encoder. So that cross attention map between the images and image tokens and the text tokens, it's going to give you like an idea of which text tokens are related to which part of the image. So they use that to create a mask, and then that mask allows only specific features that are relevant to that text to be fed into an expert, right? And because of this argmax, right, they're basically zeroing out the signal that goes into the next layer. So there's only one route that the path can take, right? And it's kind of like the same way that I had the dropout paper somewhere, but the same kind of intuition that you use for saying that Dropout is training a mixture of experts is kind of the same thing that's going on here. Because why is Dropout a mixture of experts? Because you're forcing a bunch of different paths, each of which can be kind of loosely seen as its own little sub-network. So there's kind of a similar kind of high-level intuition here, where because you're forcing specific paths, you're creating kind of many different little sub-networks in between, aka a mixture of experts, where one expert is kind of one sub-network, but they're all within the same network. So that's kind of what makes it confusing. What else? They also have another big thing that they do here is basically they do this edge supervised learning, where they train another neural network, so separate from the vision encoder, separate from the text encoder, separate from the diffusion model, separate from the space MOE network, separate from the time MOE network. They have this edge network, and this edge network is trained with supervised learning to map, or to basically convert an attention map into a edge map, and that edge map is used as an additional supervised loss when training the diffusion model. Okay, so those are the main components here. In terms of the actual final results, I think that they do show that in a human user study, so they have people actually look at these pictures and pick the pictures that they like the best, and to me that's the gold standard. And they do show that compared to DALL-E 2, Stable Diffusion, Deep Floyd, they are getting better quality images, better alignment images. So I feel like I'm comfortable saying that this is probably the state-of-the-art image generation model because of this human user study. If they would have only shown us this FID, I would have not believed their claim of state-of-the-art, but the user study to me convinces me, okay, this is state-of-the-art because you got humans to say that they agree with that. I like this little trick that they did. So they did a trick where they basically trained a classifier on the specific routes and then showed that the routes that you take can be used to basically train a classifier for specific words and concepts. I thought that was kind of cool. What I didn't like about this paper is that these figures were terrible. Whoever made these figures, like, terrible figures. They don't have all the pieces. Like the way that shit flows here is like hard to really understand. And it almost seems like they're trying to confuse you more than they're actually trying to help you with these figures. But other than that, I don't know. I feel like it was overall pretty good paper. A little state-of-the-art image generation. I don't think that they're going to make any of this available. At no point did it sound like they're going to basically release this model, so it's not going to be like a stable diffusion type of situation where you can basically get the model weights and use them yourself. This is probably just going to be exposed via an API, so similar to kind of a Midjourney, where you can go and you can pay them whatever, like 1 cent or something like that to generate an image, but you're not going to have access to any of the underlying models, which, I mean, makes sense. A company like SenseTime is probably interested in kind of getting into that generative AI space. They want to make a product. They're looking at Midjourney and they're like, hey, let's just do that. Let's make a Midjourney. So, makes sense to me. That's all I got. Surprising that the routing function only depends on the text tokens, not the text and the mask. Yeah, and then the time routing function only depends on the time, which is even weirder, right? The time routing has no notion of the content of the image. It's only dependent on the time. That was a little weird too. So down here, where is it? Yeah, this right here. The fact that the time router only depends on TI. That's weird, right? Like, don't you feel like there should be some notion of like the content of the image at a specific point in time? Right? I don't know. But I don't know, cool paper. I feel like I felt a little like not quite there yet. You know, I kind of apologize. I feel like I woke up on the wrong side of the bed and I got a bunch of things wrong. So I really appreciate the feedback, Nisio and other people that were commenting. Thank you for correcting me and helping me get through this paper. I always appreciate it. But yeah, thanks for the stream. Tomorrow we're going to be looking at a big paper from Google where they basically train a giant vision text model with Google level money and Google level scale. Hopefully they actually say something interesting. There's a non-zero chance that we read the paper tomorrow and it turns out that they just don't tell us anything, but that would be a little bit sad, but hopefully not. And yeah, that's it. Like and subscribe, join the Discord. Thanks everybody, and see everybody.